I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on the period of an oscillator using angular frequency, frequency, and period. In this video, we're going to talk about the period of a spring oscillator using period frequency and angular frequency. So let's start with what period and frequency of an oscillator are. So the period is the amount of time it takes for the oscillator to repeat its motion. So as it slides back and forth, once the object slides back and forth, we time it, see that the period of this oscillator is 1.67 seconds because it's the time it took to get back to the same spot where it started. Now the frequency is the amount of oscillations an oscillator has per unit of time. So how many times does it go back and forth in 1 second? Frequency is the inverse of period, which means that period is just equal to 1 over frequency, or frequency equals 1 over period. So that means 1 divided by 1.67 seconds would be the frequency of this oscillator. So let's talk about angular frequency and how it's related to frequency and period. So let's start with a simple harmonic oscillator and an object that is moving in uniform circular motion. So we know uniform circular motion means that it's moving at a constant speed, even though the velocity is constantly changing. So we can look and see if that we have a green dot in the center of the spring oscillator, and that lines up when it's at its maximum point. And as we set that back in motion and we pause it at the bottom, we can see the green dots are still lined up. But are they still lined up at any other point? So we can let that oscillate around and we can see that yes, at the middle point, they're still lined up. So that means those green dots are continually lined up as this spring oscillator goes in a circular path. Uniform circular motion means that the velocity is changing, but the speed is constant. So let's look at the angular velocity. We know that angular velocity is the change in angular displacement divided by time. And the angular displacement for one full revolution we know is 2 pi radians. And the time for it to go around one time is called the period. That's the time for it to repeat itself. Now, if we look at the angular frequency, this applies to our spring oscillator. Well, the angular frequency is just going to be that omega equals 2 pi divided by t. That is the spring oscillator mimicking the orbit of our object that has an angular velocity. So we look at period and frequency of an oscillator. We start with this equation. We want to solve for the period in terms of the angular frequency. So what we're going to do is we're going to rearrange this equation to solve for period, and period is equal to 2 pi divided by that angular frequency. And we also know that period is also equal to 1 divided by frequency. So we end up with this 3-part equation where period can be calculated in multiple ways. So let's summarize these 3 terms. So period is the amount of time for an oscillator to complete one cycle. The symbol is capital T, and our SI unit for period is measured in seconds. Now frequency, that is the number of cycles that are completed per second. The symbol is a lowercase f, and the unit, the SI unit, is inverse seconds or just hertz. Now the angular frequency is the number of radians completed per second. Remember our horizontal oscillator as moving up and down. We also had the circular motion, so it mimics the circular motion of something that's moving at a constant speed. The symbol is the Greek letter omega, and the SI unit for angular frequency is radians per second. And a note that 1 hertz is equal to 2 pi radians per second. So angular frequency and frequency are not the same thing. They don't have the same unit of measurement because 1 hertz is equal to 2 pi radians per second. So let's delve into angular frequency a little bit further. So let's talk a little bit further about what angular frequency is and how it affects an oscillator. So what we're going to do is we're going to look at our position time graph that we created in the previous video as we send this oscillator back and forth and we sketch our position time graph. Now it's important to note that each of these graphs is drawn based on where the spring started. So in this case, it starts at maximum stretch, which is what we're going to do for most cases. But if the spring were to start At equilibrium, that would shift our graph, and depending on if it moved positive or negative from there, it would be it would have the same shape, it would just be shifted left or right. If it started at max compression, then it would start somewhere in a different spot, and we'd have that same graph, just again, would start at a different position. So it'd be shifted left or to the right, and we'd start at a different spot. So let's go ahead and write our equation for this graph. And you should be able to recognize this graph from a previous math class. So we're going to start with x equals, and you should recognize the shape of this graph as a cosine graph. So position as a function of time is equal to cosine of t. Now that maximum value and negative x max value, well, we talked about that. The x max value, that's just the amplitude. So we're going to put a in front of that. Now here's where angular frequency comes into play. The angular frequency is going to be the value that we're going to multiply in front of time. And remember, cosine of some value needs to be a unitless number. So radians per second times seconds means that these units would cancel out. So we can take the cosine of that value in radians. Now, if we increase the value, what had happened to our graph? Well, it kind of got squished together. So the angular frequency impacts how stretched out or compressed horizontally our graph is. So that's the impact that angular frequency has on our position time or any of our kinematic graphs. But also remember this equation that 2 pi over omega equals 1 over frequency. We rearrange that equation. 2 pi times f equals that angular frequency. So we can actually substitute that in for the angular frequency. So x equals a cosine of 2 pi f times t. And that's the equation that you're going to find on your AP Physics 1 formula sheet. But just note that 2 pi f is just the angular frequency. And remember that the amplitude is just how far the spring is stretched or compressed. So let's calculate the period of a spring oscillator. So we're going to go back to the situation where we've got our oscillator moving and we've got uniform circular motion, and we're going to pause it at this point. Because at this point, the object that's moving in a circle is moving vertically. And our speed in uniform circular motion is an object moving at a constant speed is just distance divided by time. Well, the distance that an object travels around a circle is just the circumference, 2 pi r. And the time, again, to go around one time is the period. Now, let's look at the speed for our oscillator. Well, at that point, we know that the dots are lining up and they're mimicking each other's motion. So they have the same speed at that point. So that Vmax, that maximum speed of the mass, we derived that in the previous video, is Vmax equals x times the square root of k over m. Now, if we find the period of an oscillator, what we can do is we know those velocities are equal, so we can set them equal together. And we can substitute those equations in. Now, we have a lot of unknown variables, but if we look at this as it oscillates around our circular path, we pause it at this point. We know that the radius of the circle is from the center to the green dot. We also know that x is how far the spring is stretched, but that is the same distance as r, so x is equal to r. So we can actually substitute x for r. So that simplifies our equation. The x's will cancel out from each side. And our goal is to solve for the period. So if we solve for period, we multiply both sides by period. We divide by the square root of k over m. So that's going to give us 2 pi, and we do the reciprocal, square root of m divided by k. So that gives us an equation for the period of a spring oscillator is equal to 2 pi square root of m divided by k. Notice that the amplitude does not matter in this case. So if we had friction that would cause that to slow down, the period would still be the same because the amplitude does not impact the value of the period. Only the mass of the oscillator and the spring constant of our spring causing it to oscillate are the only two factors that impact the period of our spring oscillator. So let's look at angular frequency and period. So we know that period is equal to 2 pi divided by the angular frequency, and we just derived this equation in the previous slide, that the period is equal to 2 pi squared of m over k. Well, 2 pi over omega is also the period of our spring oscillator. So we can actually set these two equations together, and we can see that setting them equal to each other, that we can simplify this equation by canceling out the 2 pi's. Now, what we're ultimately trying to do is we're trying to find an equation for our angular frequency. So we can rearrange this equation, solve for angular frequency, and when we solve for angular frequency, that's going to give us the square root, and it's going to be the opposite of what we had because we got to divide by square root of m over k, so it's going to give us the square root of k divided by m. So our angular frequency is equal to the square root of k divided by m. So this is important. We're going to tie this all together from the previous video and this current video. So if we go back to our original graphs of position time, we know that the x value, that x max, is just the amplitude or how far the spring was stretched or compressed, and we derived this equation, x is equal to a cosine omega t. Then we look at our velocity time graph, and we derived this equation using our conservation of energy, V max equals x times square root of k over m. And here's why we took that x squared out, is we know that omega is equal to the square root of k divided by m, which means that we can substitute omega in for square root of k over m, and V max is equal to x times the omega. So if we write an equation for our velocity time graph, we know that this is a negative sine graph, and the amplitude of that graph can be calculated by taking x, or the amplitude, times the angular frequency. And we put angular frequency in front of time because it matches up with our velocity, our position time graph, so it has the same angular frequency. Now we look at our acceleration time graph. We derived an equation for the max value to be x times k over m. So there's that k over m term again. So we know that omega is, again, square root of k over m. But if we square both sides of our equation, that's going to get rid of our square root, and that's going to give us omega squared is equal to k over m. So that means our max acceleration is just x times the angular frequency squared. Now we can write our equation for our acceleration. You may recognize this as the opposite of what you had for the position time graph. So that's a negative cosine curve, and our amplitude is just going to be x times omega squared, or the amplitude times the angular frequency squared. So these are our 3 equations that we can derive. Now, if you're in an upper level math class, I'm sure you're looking at this and you're saying, oh, I could have done that without going through and doing all of this. But we derived these equations using algebra. And it's important to note that you're going to need to know how to do this algebraically and derive these equations, because you're probably only going to be given one of these graphs, or asked to draw one of the graphs and maybe write an equation for it, or use the graph to find the equation. So again, learning algebraically is going to be very important in order to just be able to draw a position time or velocity time or acceleration time graph and be able to derive the equation. So this is an introduction to period, angular frequency, and frequency. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below and subscribe to my channel, Happy Coaches, and follow me on Instagram and Twitter @HappyCoaches.